Okay. Welcome everyone. So this is our new semester of talks at this seminar, and today we have the special pleasure to welcome Pavol, who will tell us about phasing connection and its holonomy as morphism operads.
Thank you so much. It's a great pleasure for me to be here, and it brings great memories because I studied here in the previous millennium.
A millennium ago.
Yes. That's it. It's all a right title thing, roughly. So it's phasing connection and its holonomy. As morphisms operads. So what is it about? There will be some quick introduction. I will then try to explain things that appear in the introduction, maybe a bit of earlier later. But somehow in the beginning of time, the Greenfeld came up with this what is called now using some logical associator. So it was one of these famous associators, which is this thing. So we take two letters, A and B, and consider three algebras generated by these two letters. And then we take this kind of one form, which so it's a one form. Z is a complex vector. It's one form with values in, let's say, the three real algebras generated by these two letters, or my twist. And then we want to take the holonomy of this thing, holonomy of this connection, when Z goes moves from 0 to 1, or as whatever more physics notation might be something like dx papa, so the integral from 0 to 1. With my Z minus 1. So that belongs in formal power series, not in this power series, in these two letters A and B. Now, the trouble is that this expression is not well defined because there's some divergence. So when Z goes to 0, then this diverges here, and at 1 diverges there. So the actual thing needs to be replaced a little bit for something like expressions with some limit. When epsilon goes to 0 plus, we take the holonomy from epsilon to just 1 minus epsilon of the same stuff. So that doesn't change. And we need to regularize these things by whatever is happening at corresponding end, which turns out to be exponential of A times epsilon, this part of this, and then here is exponential of B epsilon. So this is well defined, and then it satisfies all kinds of wonderful relations. What satisfies some algebraic relations. Which are called, there is one important, which is pentagon, and there's a hexagon, and there's one more kind of scheme thing. So people prefer to write everything in explicit formulas, which is on some level good, but that it left some other people puzzled because you would then refuse to say what it means kind of more conceptually. But then people figure it reverse engineered Greenfeld. So this was done. And then later, this is the question: so what is an associator? So this one is an associator, and their answer was that Martin's answer really was that you say morphism of operad. Well, some two very explicit operas. So one of them is terminology by Barnatan is called parenthesized braids. The other one is called parenthesized diagrams. I said I will skip some details at this point, but what are these? So the thing is that for any finite set S, this is going to be a groupoid, so it's an operads in groupoids, and a groupoid is a category, particular solution has some objects, so objects are undersized permutations. That's what basically the idea is that if you take an arbitrary braided monoidal category, and let's take several objects that which we name by the elements of S, let's say A, B, C, D. I know these are our let's say four objects in an arbitrary braided monoidal category. Then one can ask what kind of operations we can do with these four objects. We can make their use product. So we can, if we have four objects, then we can do something like, I don't know, A times C, that will tensor not be writing, and let's say times B. We need to choose enough bracket things for the tensor product because it's not associated on the nose. But then because we are trading and associated with the constant, and each time we have anything else, B, A, C, D, we can choose an arbitrary trade. I don't know. It's not doing that. This one. So this would be some practicing. So this would be a morphism in our category. So it's kind of this kind of thing. And this is something which is associated to its associated braided. And how does this associated appear there? Roughly speaking, associated corresponds to when you have this move, like ABC, that belongs to the of ABC. So this is sent to our associator, which I didn't write anywhere. It will be defined for Z. It's also be sent to arbitrary associator, but that one should work. As I say, I didn't explain what it means properly, but I'll say it more. And the reason why KZ is an associator, why it satisfies this, KZ is such a thing. Because of the KZ connection. Is flat and is somehow compatible with operatic structure. Now, so this is now the problematic part when it needs to be compatible with operatic structure. This is what I will be talking about, and I'll actually give you the definition of things that are happening here. The main trouble is somehow that the holonomies, this is a holonomy for some practical class somewhere of basic connection. This will be part of the basic connection, but it needs to be regularized. and we're taking holonomy between 2 points which are not really there. We somehow need to remove those points, so somehow this needs to be sorted out. And this looks like a very technical stuff, but it makes for a nice story. So there's something nice around it. If you actually read the abstract, I think, then it contains the name Trojan net. So this thing is done with, I'm not sure whether I should call it a joint work, because who knows whether it is a work, but it's a thing. So let me know.
Can I ask a quick question?
Yeah.
So here for the category on the left side, so do you choose a graded monoidal category?
No, but this is something like a universal thing replacing graded monoidal categories, or rather, that's how I should say that a graded monoidal category is a PAB algebra in the category of categories. Okay, in the symmetry monoidal algebra. So these are somehow these are operations that are present in every graded monoidal category, and the thing is useful for some quantization problems, basically.
So an element, an object is a sequence of symbols and bracketing.
Yes, that's it. But okay, let me now kind of restart. So I will talk about for some moment about the basic connection. Basic connection is on some manifold. So at first I'll tell you which manifold I have in mind. So this will be what we moduli space of frame mark curves, which sounds horrible, but what it is something very simple. So let's take CP1. CP1 everyone's here. And look, I have someone got to use them. So I will pick there will be some finite synthesis. So let me choose several points in CP1, and they will be a little bit bisected by these elements from S. So let's call this like now. Let A, let B, let C, and S is equal to ABC, for example. But on top of that, at each point we choose a non-zero tangent vector. So this will be like E and okay. So let's take these kind of configurations for this thing done modulation of the SLPC. So that's our space. It's the same thing as that thing.
Just rational figure.
Rational just it's genus 1. Genus 0, sorry. There is a curve of Riemann surfaces, compact Riemann surface of genus 0 with these marked points and vectors, and up to isomorphism with this SLPC. So what does it look like? Let's say I'll call it. No, these things are it's modular space without framing. It's called, for example, M0 of N, where N is the number of points in S. For but it's framed to the F. And typically, I think now we're forgetting this 0, but we'll never identify these things. So what is the simplest non-trivial thing is F M02, or with F M whatever A B. This means when this is S. So in the case with just 2 points and 2 tangent vectors. So this thing is the naturally isomorphic with C star. Oh, you can imagine we can move 1 point to 0, the other to infinity, and then do some scaling. Or that's roughly speaking like a kind of cross ratio thinking. If you want formula, you don't, but anyway, I'll write it. So the formula is that a PB is not to B Z A minus ZB squared. So that's it. In case we the formula is up. But anyway, so in this case, it's just this. But then
So how does the scale impact on the vectors?
So-
On the tangent vectors, how does the scale impact?
scaling.
Yeah, you said, for example, in this case, you can, there's still scaling inverse of 0 and infinity.
Okay, so yeah, so there's still, so then it will it can arbitrarily rescale the tangent vector at 0, but it will also rescale the tangent vector at infinity with the inverse of the scale. And so yeah, you can fix the tangent vector at 0 to be the standard one, but then the one at or vice versa. And the other one will be arbitrary number in C star. So that's
So that just would be induced by the SO2 selection on the surface itself.
yeah. Oh, yes. Yeah, I mean, this acts on tangent vectors on naturally like the tangent. Okay, and now if you have so this gives us that whenever if you have a larger S and if A and B is a two-element subset of S, so then this gives us a projection. So there is a map going from F S to F AB. Just the forgetting map when you forget all points beside except for A and B and stuff vectors. So let me call it, I don't know how to call it. I'll call it PAB. So it's start. And then that KB connection of framed so what is it itself? Something A, I should write some A, K, Z, and S here. This should be a one form on our moduli space of F and S with values in some suitable algebra, which I need to explain. So with values in some algebra FTS. How is it given? There's kind of easy formula that is missing.
So this modular space, what's its dimension? What is local dimension?
Dimension is this is for two. If there's two, there's two stars, and then yeah, and then so then each time we add one more here, then we're introducing 2 dimensions because we're introducing one more point and one more vector. So it will be choice. So yeah, so it's like n minus 2 and minus 1 or minus 3.
2 is minus 3. No?
2 and minus 3 sounds better. Yeah, some whatever data entry. Probably, except when it's equal to 1, then its dimension is 0 or minus 1, depending on how probably one counts it. But anyway, so what it is, this crazy connection is just very simple sum over all these two element subsets over all yes. And then there is some generator DAE, so this is the thing which belongs to our the algebra. Times we take this projection PAB and pull back an natural form from here, natural one form is just dw over w. This w is the coordinate. W. Yeah, and these are generators. Yeah, I spent maybe more time than I should have on this connection, but many of you definitely know about this connection, but this is the right one. So there are various versions of this, but this is the one which actually appears in conformal field theory, where those vectors, and we can change these vectors, they correspond to conformal weights that we can have at those points, and it's supposed to be whatever it is. So SL2C basic is supposed to be distant to the quotient. Okay, so let me still spend even more time on that. I didn't say, oh, yeah, I said there is some real algebra, but I did, which is generated by its KABs, but I didn't explain what the real algebra is. So I should be using the what razor?
Yeah, water is better.
What is better?
Well, that depends on you, I guess.
Okay, no, I just don't know what's the. So, no choice.
Water is better, but it takes a time. I mean, maybe not now.
The result is there like split doesn't appear somewhere in the
So, yep, so in when we take a particle representation of that, then these something will be appearing in this company. I'll get with track of it. Well, I probably pleasure with using this.
You can also do things, but I'm very So the conformal weights correspond to the vectors, or
Yes. Let me get with so what is I wrote also your so spoiled it. What is FTS? So this is generated. What is this real algebra? It's called frame Greenfeld Kono. No, I'm not sure if it makes no sense to write it down, but it's a nice real algebra in dimensional, so which is generated by this TABs for every two element subset. There is one generator, and the relations are that TAB, TCP is equal to 0. If they are all different, and then there is one relation, which is the sum over all, I don't know, B's in S. Let's say B depends on A of TAB. Let me call this CA, but this is central. So these kind of correspond to those conformal weights at those points. And one thing which is happening now that if you actually keep those points fixed, if I'm going to Z A, Z B, Z C, they are not moving, but we're just rotating or just changing those tangent vectors. So what we shall see something that A. Let me use some other. that is fixed. Then that Z, I don't know, S will look like, well, maybe up to some coefficients, sorry, I don't remember, but it will be something like sum over all A's, and there is this VA and VA over. So these central things, they correspond exactly, they are coupled exactly with changing the width of the tangent vector, so they feel these conformal ways. And if you are somehow represented using some quadratic degree algebra, then the DCA would correspond to the customer.
Some the algebra of some group matrix group with and it is non-commutative, just free. So we have a S by S matrices as the elements and the non-commutative free algebra. Will be the algebra of this.
Okay, I don't know. Okay, so sorry, I don't.
Okay,
There is something like that, but okay. And it is some infinite dimensional algebra. This thing, and it has many representations.
no, I mean,
And one of them is there is some permutation thingy somewhere. So this is one of many like.
I was curious about the corresponding Lie group.
This okay. This is always infinite dimensional. I mean, as long as at least three, and has at least three elements. So it's a Lie group kind of exists. So it's a from the total Lie algebra, but it's infinite dimensional. It's not very bad, but it is. Okay, so this was a very long explanation of what AKC is. Now let me get to the actual program, or to which I mean I want to at least define stuff that was in the introduction.
Yeah, but a quick question to this Lie algorithm. So for the Grünfeld-Korno algebra, I thought there was an additional thing that you have to ask, like the commutator of like 1G on the left and the special G on the right, or is the
So for people who actually know about the true Grünfeld-Korno, so how does it work? The thing is, we would choose one of those elements of S to be kind of pointed or to be infinity. So we just move that, we just specialize that point goes to infinity, and we don't talk about it anymore. It's just hidden there. And it kind of also restricts a little bit this group number, or this tangent vector is also fixed or something. So we can only basically translate stuff. But okay, so we kind of lose one of those labels. So then we're using only PABs, but with those remaining labels. So AB are not supposed to be that infinity label. And then when you rewrite it in this Lie algebra in those terms, then it turns out that it's enough to use just PABs with these restricted generators. They will generate everything. That's fine, and you will get like what is a Grünfeld-Korno. You will get also this additional relation in Grünfeld-Korno. It will come from this centrality when somehow this term contains also when B is infinity, and then somehow like things get entangled a little bit. So it will be like Grünfeld-Korno, but plus there is additional, there are the central elements still at those points. So yeah, this but anyway, this additional Grünfeld-Korno relation which contains 1T and 2T's here, it will follow from the centrality of the thing.
Interesting.
Okay, it's a type of light. Okay, so let me now get to the program. And if I get to the problem, I think it will be already a small victory. But okay, let's at least try to describe this thing. So, we have now three objects, so to say. One object is this family of those frame marked with modular spaces, so those F and S's. Another object is this Lie algebra, and they are kind of bound together using this crazy connection.
So the connection is flat.
Yeah, this is what I should have said, of course, the connection. And it is as AKCS. And yeah, and you can like these relations are equivalent to flatness of one or that function. Okay, so what I wanted to say now that this F and S is they want to be a cyclic product, and these F T S's actually are, or they form. I'll explain what I mean by that. Morally, this is okay. It's almost a cyclic operad, but I need to explain what the cyclic operad means, and what it wants to. So what does this thing mean? So imagine, let's say two sets, S and D. So it's like F and S, and let me add there one more mark. So let's take this slightly bigger set, but there's one more like star. And times F and E, and together with one more point. So a cyclic operad structure would be the thing that we have actually a map going to F and S is going to be a E. So what would it be? No, being a cyclic operad means that for every finite set we have a space, let's say this one is in the category of manifolds and non-manifolds. It should be like stupidly functorial in S, which just means that if you have an isomorphism of bijection between two finite sets, then we should have also corresponding bijection between those sets. That's fine, right? So at least it is the stupidly functorial that is. But then we need to also have this kind of maps. For every S and T, there should be a map where somehow, here there are these two stars, they kind of, here and there, they kind of disappear after that. And these maps, there should be some naturally in S and T, that's fine, some relabeling should be there, but it should be associative. So if you have three things, then we can glue it either first there or there, it should be the same thing. And it should be sort of commutative, that if you exchange S and T, you should get the corresponding map again. So that's the definition. But why does it want to be? What is this map in our case? So let me take a point here, and that point here, so a point is a particular configuration. Right? So it's a particular thing like that. There are these points, then there are tangent vectors. And let me specify, this is the point which is marked by star. This might be something, I don't know, ABC. These are elements of S, this is additional thing. Now, let me do the same stuff here. So there's this thing marked by star, it might have some tangent vector here. EF and tangent vectors. Now the fact that we have tangent vectors here, they mean that it doesn't really specify a local coordinate around the point, but up to first order. So one can imagine that we have some coordinate z, which is equal to 0 at this point, and so this vector is d over dz. It's only defined up to first order, but that's why this they want to be a cyclic operad. They are subtly failing.
It's just a curve nearby, it's a curve through this point.
Yeah, okay. That's right. So so now imagine that we actually take some, I don't know, coordinate z1 around here, in the vicinity of this point, and coordinate z2 around here, which is somehow compatible with the tangent vector. And then we use them to we cut out some very small disks around it, and then we glue it. So basically there is this kind of operation after that.
Connecting some.
Yeah, it's a sort of connected sum, or which is yeah, that's it. So which is so what we're doing here that we want to the way how it's done with this identification is that z1 times z2 is going to be a constant, right? That constant is some epsilon squared, where epsilon is not something supposed to be small, actually infinitesimally small in the end. So, but so these maps are kind of almost well defined, but only to first order or something. So this is not quite. Basically, we're sending the pair of these 2 points to some kind of ideal point here, to a point which is not truly there. So where this whatever tunnel is infinitely whatever narrow. So
You somehow relate this to the arrows are aligned, how you use the information about the mutual line direction.
Okay, we use this. Okay, we can always turn it to the line, but I mean that's the way how we glue it. If they are not aligned, we simply when you're gluing those things, we turn one of those openings. So the kind of moral is that we need some ideal points. To these people, and what in this case it is this general. So some kind of ideal points need to be added so that this operator decomposition actually makes sense. For some infinitesimal epsilon, it's not difficult, but it's just quite difficult.
So you are gluing the special points, or you are?
Yeah, there were these 2 points which were both of them marked by star. So we're gluing those or like those infinitesimal neighborhoods of those points together. Yes. So that's why this star disappeared in the end. There is no longer any mark point after.
And so if you do it like this, then none of the results of this composition will be like all of them will be ideal points in the right.
Yes. We never get to a non-ideal point, except okay, if whatever if this has only 2 points, there are some special cases which I leave to you as an exercise to think about how to do it. But it is right. That's the general.
And you assume SNT to be disjoint, and I mean, otherwise it's really.
I make them kind of formally disjoint afterwards. So you rename them or something.
And you also kind of always move with SL2C so they don't intersect in the CP1 either, or does this?
It's not. No, like what I obtain after this is okay. There are 2 ways how to think of it. So if you actually would take 2 Riemann spheres, super Riemann spheres, and you cut out small true disks, geometrical, whatever caps, something, and glue it, then you can measure now identify this glued surface again with a new of Riemann sphere. Okay, and that's what's happening.
Okay, thank you.
That's correct. Your star, like in both of these pointers, is up to really, they could be different up to the action of the soul to see. So you do not ask them to be the same up to the action of the soul. So it's okay to feel.
Sorry, I kind of call them 2 of
Yeah, so it's star primes.
yes.
That's
If it's less confusing, I'm very happy to tell you that. Sure, but start by this. Okay, so these people really want to be cyclic operas. This is what those types are, and I hope it's visual enough to actually explain the definition of a cyclic operand. That in the end, yeah, cyclic operand is a simpler thing than an operand. One can say it's just maybe operand with more structure, but cyclic is also something which is easier. Okay, so I said that those spaces they want to form a cyclic operand. And those, then I wrote that those 3 algebras, they actually are a cyclic operand. So let me write that. That's obvious, but Oh, but at least it's easy to do. I think this is sorry,
Oh, turn to the right, I think. So you need to turn to the right. Yes, like that. Okay.
like that.
Yeah, that's cool.
Yeah, don't worry.
Yes, this is called.
Okay. Well, what is what I think?
Okay, maybe it was the other way around. Sorry.
Let's go run with the assembly.
I think it was very counterintuitive, but I forgot which way to do it.
Excuse me, maybe another line of question. The transformation of two kind of infinitesimally connected CP1s into an ordinary CP1, it's not holomorphic, right? You or like it would just be some diffeomorphism.
Oh, it's a holomorphic.
Okay, okay. But
I mean, you get, okay, so if I want to say it like very analytically, you get a surface with genus 0, and therefore it's isomorphic to CP1. In a non-canonical way, but up to SL to C, which we anyway throw out. So
okay, thank you.
But maybe put another way. You know, if you have a Riemann sphere and take off a cap, I mean, you draw there a circle, then you can always find the Möbius transformation and something from SL to C. It will move that circle to the equator, and if you do it with the same stuff there, and so then you end up with just two half spheres and you glue them. But if you do that, I mean, if you imagine there was a small circle here, and you expand it, and this point would kind of shrink. They will go like together here and together there. But that's also a way of how to try to understand the outcome of the sphere. But all these mark points are really infinitely close together here, and these other are infinitely close together on the other side. If it helps. It's something to make it fun. Okay, so this is just some symbolic thing now. So this, as I said, it's ST S6 that form a cyclic operad. Well, in the category of the operas. So now I need to tell you again this kind of composition rule. So we have going from FTS together with some star and sign plus FT together with some star and star prime matter going to FT as disjoint T. And so what is it doing? We have to say where the generators of this guy are mapped and where the generators of this guy are mapped. And so we just take generators here, we take TAB, that's being mapped to all the way there, just the TAB. So this is A and B in S. If there is no star in it. But if you take a star, so that's the other possibility that we actually use this guy, then that star is going to be replaced by the sum over all elements of T. So yeah, up to the sum over all, I don't know, P in P, nothing spectacular. Okay, and now the claim is somehow, okay, we have these two operads, one of them is true, the other one is fake, it needs to be repaired. And they are related through this basic connection. And that claim is that somehow this crazy connection is compatible with those two operatic structures. And Z or wants to be compatible. This needs a bit of explanation. I will still get to it. So the talk is coming to the end, but let me actually tell you something. But maybe before launching into that, it's one thing I wanted to. Oh no, okay. Let me pause this. So as I said, we need to add some ideal points to these spaces. First one is ideal points. So what are these? These are also known as tangential base points. Might have several other names that were introduced by Derry. So, but what we want? So we have our, our space F and S, and now we enlarge it. So we add more points. So we get a bit bigger points. The space of ideal points. FMS. That's the space of ideal points, which contains more points. We want this thing. This is a topological space. What you call we don't care about more structure, it doesn't matter. But at least we want this inclusion to be a homotopy equivalence.
Is it some kind of compactification?
Let me get to it. It is some sort of compactification, except that it's not quite. So let me explain this. What this is on an example. So what is I of C if C is a punctured curve? So if C is equal to some, so it's a curve and minus some point. So what will be happening here? So in this case, so our curve is something. Here is our, let's say, compact curve C bar, whatever it is, whichever genus it might have, and there is this function. Then it's IC that's equal to C itself. These are the ordinary points, but then there is union with TPC bar. Sorry, the tangent space at this point, but where we remove 0, so minus. Okay, this is what it looks like. For the moment, it's a bit strange. But what is the topology on this guy? The thing is that there is a compactification of this guy. As I mentioned, there is something which is called the real oriented block. So let me draw different stuff again. Where we replace P by a hole, by a circle. This is what is the real oriented block of the C bar at P. And what it actually is, so this simply is the same, the good old C together with this new circle which appeared here. And how do we obtain the circle? It's simply, these are simply the tangent vectors minus 0. And but where we care only about the angle, we don't care about the length. So we mode out by the epsilon r plus. And it comes with the nature of topology. I mean, this is just the surface with boundary. And so here we have now the projection, of course, I mean, that's the projection. And the topology here is pulled back from here. So open sets are those that are pulled back by this map, which means that this space is horribly non-Hausdorff. But that's the way to do it, it turns out. So it's kind of, but non-Hausdorff. So not sure whether it counts as a compatibility. But that's what it is. I mean, in general, yeah, this is what's happening in dimension one. And in general, if you imagine you have a product of several things of this form, and this construction of ideal points is going to be compatible with products, and so it will work for whatever device precision, normal cross things or things like that. So just to give you some idea of what's happening. Okay, so this will be the ideal points. The statement is that out of something, some structure which was undisclosed for the moment, the space of ideal points, so these would form a true operad now, a true cyclic operad. This one wanted to be a cyclic operad. This here we now added those points which now make it to a cyclic operad, but it comes from some holomorphic data which I didn't explain, but it's still good news.
It's the macro question.
Yeah.
So whatever happens here instead of the conditions that you described, looks for me like very much like making a nodal curve, like for example, in this normal compactification business, right? So somehow is this type of compactification in a way related to the
It's a very pertinent remark that and the thing that I probably should have said. So you're right. If you like really shrink this to a point, it becomes a nodal curve. But we want to still remember a little bit more somewhere, and that little bit more is that our map. No, so like there are those. There is this what compactification thingy or something, and there is that divisor of nodal curve. And where this map actually goes, it wants to avoid the D. We don't want to go to D, but it goes infinitely close to it. So it actually goes to the normal bundle of D, but minus the 0 section. So in that sense, it looks like this. And that's what's happening here when I have to add C, the normal bundle to that point minus the 0 section. So it's precisely that.
Is that epsilon squares in the brewing kind of conditions? You want to use epsilon square, so you fix that one, or you kind of add epsilon?
Well, epsilon is something infinitesimal.
Okay.
So we still like algebraically infinitesimals, which like something. Or maybe it's called epsilon squared or epsilon. That doesn't really matter. Okay, so this is a true cyclical graph. Let me at least get to the result, even if I don't tell you how it's done, but it's not so important how it's done.
For example, this you called this A KZ this way because it's attached to the hyperplane arrangement of type A, or just
A is just the kind of standard name for a connection.
okay. And
No, there's no reason for calling it A other than just the first letter of the alphabet.
the second question is what about the other types? Like, can you do the same?
No comment. Third type. No, I don't know. I'm not sure. Right. No, yet these people they form these cyclic operads and thingies. I'm not sure what those for those other type of braid groups, whether they form. Probably they do, but I can learn about it. That's what I can say. Okay, now the second thing is, we had our crazy connection on these people, so that I can use on those F and STs. But let's go to those ideal points. So somehow we need to extend it to I, F, S. So how do we do this? But it's IFMS, okay, it's sort of manifoldy, but it's a non-has the topological space at the same time. So what do I actually mean by that? So the way how to think about this guy, a flat connection, is that if you take, let's take the let's say the trivial principal bundle over this guy. So we take those groups, I don't know how to call it. FPS, that's the group corresponding to F little PS, and times these are such long names. This over S, let's say trivial trivial bundle for this group, and the flat connection will give us these parallel sections on this stuff, and we can now use it to turn this map to a covering map. So let's turn it to a covering. It requires we need to change the topology on this guy. Just use the those. Those local parallel sections to be like copies of things from down there. So now we can make this fiber to a discrete group, and this will be a what's called normal covering or Galois covering. And the statement is okay. So this is what is given.
So this is a Barney group. FPS if it exists.
Okay.
And let's describe the topology and your covering.
Let's say this is I wanted to avoid such stuff, but this is a pro unipotent group. So I think once you think of it as in a super algebraic way, at least I don't
topologic way.
Let's say okay. The thing is it's a how to put it, it's a projective limit of some system of nilpotently groups, so finite dimensional. Yeah. So yes. Yeah, okay. So that's the same. And so then one somehow can think of it fully formally just. That doesn't make sense.
Yes.
Basically, that if you commute iterated brackets after whatever with length more than n or something, that turns to some finite dimensional, and we can do it systematically. Okay. Well, so sorry. It's,
I thought that it is something different as group. I thought it is really dimensional from the beginning.
Okay.
But it is only finite number.
Yeah, well, let's see it as limit of finite dimensional ones. So it's something reasonably simple, or simple to work with. Example, not very non-analytical logic. So anyway, so as I said, we turn this to a simply using a flat connection. This can be changed to a covering, and then the statement is that actually statement of plane this extends canonically to when I replace this guy or that guy, these two. So these two guys, when I replace them with those I. So that's the claim. Now I should tell you how. Fortunately, or unfortunately, I don't know, I'm a bit out of time. But let me still spend just 1 minute for one specific example. One very quick example. Okay, so like this, this extends, and then this is now discovering topology that is actually compatible with the, and it's called, but this is operand. Compatible with operand steps. So what can we, just to relate it back to the different associator. So let me start with the 3 points. Like this is an element is in F whatever 3 or 0, 3 or so. So it's ABC or AB something. So we just can measure these 3 points. They can put 2, 0, 1, infinity, and let's just choose these vectors to be in such a way that it's in line with respect to secret permutation that we can do. Otherwise, it doesn't really matter. So there is some kind of nice particular element here. But let's not try to obtain other elements by using that opera decomposition properties. So when we do it, we can do 2 things. And we glue it here. Now we create a small tunnel. We might have something like this. Let's call it C. Or we can glue it this way. We can take 2 such things and glue them this way, or I will call it. Now I will use all those labels. So these are A, this is B, this is B, this is C. So both of them, they are in FM A, B, C, D. And in the ideal space, right? So we have now this ideal point. And there is a path between this and that. When we simply start kind of expanding this tunnel, and then we start shrinking it in the middle. So there is a homotopy class of paths. And the path here, we restrict to the covering. So this path covering. Yes, so this is our S. And when we leave the path to the covering, we get an element of our group. We just move from one fiber to another one, but they are trivialized, so we just move by an element. So this gives us some kind of holonomy. In F, T, S. And with that, this holonomy, this is equal to phi KZ. And the idea how to have all those possible braids is to start gluing this kind of spheres with 3 mark points in all possible ways. So in that way, you can imagine that gluing them, it corresponds to having a trivalent planar tree or something like structure there, and each time we have a function structure so over time. So each time we have a trivalent. If you choose any inner edge which corresponds exactly to this tunnel, so we can then locally replace it by this. So these are these kind of moves corresponding to this line. And okay, so that's roughly the story. And then there is the second part of the story. Which says why this true, where it comes from, which I didn't explain at all. But okay, that was what I expected. So that's all.
Questions?
this an operatic notation of the triple zones? You know,
These are those ideal points. They are really those triple zones. And in the sense that the ideal point which are obtained by simply composing this stuff. So these trivalent planar trees, they correspond exactly to triple zones, though for this slightly modified crazy connection, for this slightly bigger frame crazy connection.
Yeah, so I did not really understand the last part here. So it seems that there's some vertical composition and some horizontal composition of these spheres. And now you're saying this corresponds somehow to the associator that I think of, yeah, three things, and I can bracket them in different ways, and it tells me how do I move from one bracketing to the other. So how?
Okay, yeah. So the idea is that it's basically how one passes between that. The idea roughly is that you choose one of these points, let's say B, and you call it whatever, infinity. And this would be like our output. So if we associator in, as I do it here, so if I put it this way, so it's something I can move going from this, but no, this corresponds to one sphere. And this corresponds to the other. Yes. So the thing is that we're moving from this to moving between this and that. And if you choose that one of those points is infinity, one of those labels, it's infinity, and it is now A, B, C, and this is A, that's how I call it, A, B, C. So the parenthesization is that first A and B are parenthesized here, and then it's parenthesized with C. And whereas here it's that first B and C are parenthesized, and then it's parenthesized with C. So somehow, basically, we're turning our just planar tree to a rooted tree. So then you can somehow read off the parenthesization out of that.
Great, this makes.
Okay, so that doesn't make sense. Okay. It's just that the full story has some more symmetry than one would expect. Somehow it turns out that it doesn't matter whether we call that point infinity or something. There's, but parenthesization is sort of a little bit red herring, so to say. But there is it's actually about those planar trees and okay.
Is there a property of the Greenfield associator which reflects this identity symmetry?
Yes, but I don't know how to. There is one way how people sometimes write those pentagon and hexagon and they're using slightly differently algebra, but when it's like this framed Greenfield cone, but when they set those central elements to 0. But okay, it's let's say it's not a big deal. But then when they write pentagon, it looks wonderfully symmetric in the sense it really, like all the sides of the pentagon are kind of the same. And the same is happening here. If you don't do those, if those central elements are still central. So there's like also for a hexagon, or maybe that they're writing some triangle or something. So there's those defining relations of what an associator is, which looks slightly non-symmetric. Those what are 5 terms, they all of them look a little bit different. Then all of them will start looking the same. It's not a good answer, but that's the best I could produce.
So where does this come from?
No, you shouldn't stay here for another hour.
Like 1 sentence answer?
No. Okay, one can say that. Yeah, one can cook up some. That one said that those FMSs they do form an opera, but in a slightly different kind of holomorphic category. Where we add more maps. So when we have the same objects. Objects would be whatever a holomorphic manifolds with divisor with normal crossings or something. But we allow for some kind of new maps which send things infinitely close to the divisor in some sense. And it is built using we just hook up some monad on the original category, and then we take the corresponding class tree category, and so you didn't want to know. No, it's sort of it's a nice thing, and out of that one there are some functors that from this bigger holomorphic category that will produce these topological spaces, and I don't know, and those coverings. Yes, sorry, I should have prepared it as a proper talk, but it's more favorite.
If I might ask one more question, so then for as you mentioned, the Grünfeld associator has some properties like the pentagon or hexagon and so on. Can you somehow see these properties in terms of the AKZ of the connection?
Okay, so what one can say is that we have that flat connection, or then which is extended to this whatever ideal stuff, but let's just think of it as a flat connection. So therefore we have when we start talking about the holonomy of this connection, then it really gives us a map from the homomorphism from the fundamental groupoid of our space, to the group, to this group.
This I understood, but can you see kind of the pentagon property of the associator? Each sort of properties of the connection.
For the pentagon, it's quite easy.
Camera started following you.
Yeah.
Oh, I don't sorry.
No, it's okay.
I think it was after everything was written.
Yeah. Sorry, I was too much hand waving. Yes, so for yes, let me draw this diagram. That's okay. Yeah. There's a diagram which corresponds to grouping those spheres together. So there are 3 spheres here. It's this one, and this one. So it's a little bit dual thing. But and I don't know, A, B, C, D. Now doing a Grünfeld associator, like it means that it is a particle point in our modular space. That's this kind of ideal configuration. Now we take a path where some of these things are coming together, and then we get this other shrinking. So you get something like, sorry, I'm not prepared for this. So that's why it's going to be. It's a B, C. So I'm going from here to there is one little path in our thing. And then we start, so that we apply it here, now we apply it here. So we get yet another 3. But all of that is happening, there are just still only those 5 points nicely laid out along, let's say, big circle on the, all of this actually looks like that we have our basis units here, but everybody is these two are maybe close together, and this one is a little bit farther apart, and these two are close together. And so during all these moves, there's just simply nicely moving out. So it's a simply connected subspace in this configuration. So this loop that we go through, which has 5 elements, this is a pentagon. So it's contractible. Therefore, the total holonomy has to be this one, and that's the pentagon. It's not different in any way from Grünfeld's original explanation. But okay, it is what it is.
Can you prove that the space is selectable?
I mean, it's okay. So it's homotopy equivalent to the space of configurations on a circle, or something. Yes, module or something. There's sort of nothing to prove.
Another construction by Grünfeld is kind of the opposite. So if you have a quasi-symmetric category, you can hook up with the algorithm like Euler and other break monoidal category, and I was wondering if you can interpret this construction with this mix.
So, or if I, or is the question like
Like the inverse, basically. Construction.
okay, let's say, let me not answer your question with something that puzzles me. I don't quite understand. Is that if you're adding this extra symmetry to that stuff and those like that is a cyclic operad and all these framing thingies, then this is no longer just about braided model categories. It's about some stuff with more structure. And I'm quite puzzled about what it actually means. Sometimes I think that, oh, it's obvious, and sometimes I think that, oh, but it relates to something which is just trivial where nothing ever happens. Yeah, so I don't know. I'd love to know.
Okay, many thanks for the question. And thank you very much.
Let's go.